Good afternoon. It's been really fantastic to see you all, and thanks for the invitation for this. So when I proposed this, I had some very grand plan of talking about everything we've learned in the last 2 decades about Sumatra since we just went past the 20th anniversary of the 2004 Indian Ocean earthquake and tsunami. I realized that that was really not possible in 20 minutes. And so I've retitled this, and I'm going to focus on the role of the oceanic plate in influencing tectonic behavior at Sumatra. And I chose that because it was one of the areas of Sumatra research that Paul was really very interested in. He didn't work a lot on Sumatra. He gave one talk, and I really wish we could get the slides for it because it was a 1 hour brown bag of everything Paul was wondering about Sumatra, and it had an incredible array of questions we should still look at. I imagine those slides are somewhere on the desktop of his laptop, which his students will understand. It involves like 1 million files on his desktop. It would be amazing to get those slides because he had such interesting ideas. But anyway, one of the things that he really was quite interested in was how important the oceanic plate was. So I've put up a few key points here. The first one being that since the 2004 earthquake, we've really understood how important the oceanic plate is in accommodating some of the oblique plate convergence at the Sumatra subduction zone. Secondly, that understanding the geology and the structures on the subducting oceanic plate is fundamental to understanding earthquake behavior on the megathrust. And then finally, that it's been really interesting to see the conversation between the Wharton Basin offshore and the overriding plate and what's happening on the megathrust. Just to orient you, since we've been mostly talking about places further north than this, here's Sumatra. You've got the Indian-Australian plate subducting underneath of Sumatra, and the Wharton Basin out here. The colored areas are the rupture patches for the various great earthquakes that have happened since 2004. And you can see that pretty much all of it has ruptured at this point, except for the Mentawai seismic gap that continues to worry us and is offshore of Padang, which has 1 million people living in it. If you look at the oceanic plate, it's geologically very interesting. If you could go for a hike along the seafloor on the Wharton Basin, it would be a very interesting hike. There's a lot of topography, and you see these big north-south trending fracture zones that are left over from this being a spreading center in the Eocene. So this at the megathrust is what is getting subducted. And the thing that really sparked interest, of course, in the Wharton Basin was the 2012 earthquake sequence, one of the biggest strike slip earthquake system sequences that we'd seen. This was interesting to work on. This 2015 paper, it had the co-authors included Paul and Kerry C. and Thornley. So nobody had particularly strong opinions about anything on this paper, I would say. But the big contribution that Paul had was that when this happened, we didn't really know what the faults looked like that had generated this event. And so he spent a lot of time staring at the data that were available and trying to figure out where those faults were. And so the black lines that you see here were Paul's estimates of where those faults were, and then we tried to model the geodetic and seismic data using those. And actually, the data would have preferred slightly different fault locations, but Paul was really determined that this is where they should be. And down the line, Satish and Gruho and everyone went out and prove Paul right that yes, this was where the faults should be. And part of the reason that he was really excited about this was this idea that we were watching the formation of a new plate boundary forming. And that comes from the idea that the Indian plate is heading north towards collision, whereas the Australian plate is subducting under Sumatra. And it's a lot easier to subduct under Sumatra than it is to hit the Himalaya. And so you have this gradient in rates across the Wharton Basin. So it makes sense that there should be a plate boundary there. And it's been diffuse deformation so far, but the fact that this event was so big, the fact that it was very deep, it ruptured right into the oceanic mantle, got Paul very excited about the idea that we were witnessing with our very own eyes the formation of a new plate boundary. So going on to this first question, the idea of the oceanic plate accommodating plate convergence, if you look at this left-hand side, this was the more traditional view of things. And it was assumed that the oceanic plate was rigid, and then the megathrust and the Great Sumatran Fault, which runs up the mainland, a big strike slip fault, were accommodating together the oblique convergence. And to make this all work, you had this deforming sliver plate up through the middle, which in terms of the older views of this was backed up by the idea that older estimates of geologic slip rates on the Sumatran Fault increased from north to south so that you could accommodate stretching in that sliver plate. And then because of those big earthquakes, we had a lot of discussions about, okay, this idea of a rigid oceanic lithosphere is clearly wrong. Let's rethink this. And this is a paper from Kyle Bradley, where he re-looked at this. And one of the important things he did was to re-look at the geologic slip rates on the Sumatran Fault and establish that actually they're pretty uniform along the length. So your sliver plate has to be behaving in a pretty rigid way. And then how do you accommodate all this? And he did block modeling. He used geodetic data. He used the geologic slip rates. He used earthquake slip vectors because the slip on the megathrust isn't actually entirely thrust. And so you need to allow a little bit of obliquity on that. And essentially showed that the Wharton Basin and the oceanic plate play a significant role in accommodating the plate convergence. It's not all happening east of the megathrust. So my second point is that the subducting structural features influence the earthquake behavior on the megathrust. And here's a picture from Denton Jacob. You can see that these big north-south transforms represent really big steps in oceanic plate age and thickness and density. So wherever you're subducting one of these big transform faults, you're subducting a really big change in the oceanic plate. And so it makes sense that that's going to influence things somehow. And just a close-up of what is being subducted right up at Sumatra. And I included this figure for Paul. It's something we've never looked at, but the other point that he made regularly was that you're also subducting big changes in the plate spreading rate, which would influence the smoothness and the nature of the crust as well. So he often had questions about whether that difference. But by the way, this figure's, to me at least, it's backwards, and the land is the pale grey. So just to orient your eyes, and the dark grey is water, and then these colours are the spreading rate that you're subducting. But that's a question for somebody to think about: is does that matter in terms of controlling megathrust behavior, because this is what you're subducting. And what you see here are data from coral microatolls. So this is work that's done by Aaron Meltzner and Bel Philibosian and others. And corals essentially measure relative sea level. So they measure changes in land height. And so if you have corals right over the seismogenic zone, you can measure when there were earthquakes and how big they were. And the orange lines are what they determine to be persistent barriers to rupture. These are places where the great earthquakes, the ruptures did not pass through that at any point in the earthquake record that they have going back many thousands of years. So as an example, the one here, this is the Simalou Saddle. It's consistently been the southern termination of ruptures that look like 2004, and it's consistently been the northern termination of ruptures that look like the 2005 Nias earthquake, and so on. And these persistent barriers to rupture correspond with places that you're subducting these big north-south trending transform faults and these jumps in the makeup of the oceanic plate. So here's zooming in as an example. So this line here is the Simalou Saddle, we call it. It's the subduction of the 96 degree east fracture zone, and it's the southern termination of 2004, northern termination of 2005. At the southern end of 2005, you have the investigator fracture zone being subducted. And then this low slip patch of 2005, which seems reasonably robust, and in fact seems reasonably persistent over earthquake cycles, is the place that the 96 degree east ridge is subducting. And you see varied seismicity at these subducting points. So here's an example for the investigator fracture zone, where you can see this band of concentrated seismicity that goes much deeper. And the focal mechanisms for these deeper ones are not megathrust earthquakes. There's something in the slab. Another interesting thing is that you see is that the places that you get these subducting structural features and persistent barriers to rupture, the slip is very diverse, and much more so than off of those features. And so giving an example for the subduction of the 96 degree east ridge, it's this low slip patch in 2007. And that patch has been filled in by a 15-year-long slow slip event that was recorded by coral data. These, what we call sibling earthquakes, but they're essentially repeating earthquakes, but of moderate size. And then up dip of this, the afterslip, which is another thing I talked about quite a lot with Paul, because if you could go and dig a trench right up here, and you might interpret it as co-seismic, but it's actually very rapid afterslip following this event, as far as we can tell. I wanted to show this just to also show the persistence. So the inner circles are the coral uplift observations for the 2005 earthquake. And then the larger circles are the 1861 earthquake, which was the previous earthquake for that earthquake cycle. And you can see from these that they look very similar. They are very similar ruptures from cycle to cycle. And the observations for 1422, the cycle before that, also look very similar. There's just fewer observations. So on the final point, the conversation between the Wharton Basin and what's happening on the megathrust and in Sumatra, first, you can see that there was a clear uptick in seismicity in the Wharton Basin following 2004. So if you look at the figure on the right from Kelly Wiseman, this is post 2004 seismicity. So you went from some level of seismicity, but not, it wasn't nothing, but it wasn't much, to a very sudden increase after the 2004 earthquakes. Conversely, in the other direction, these are the geodetic co-seismic displacements for the 2012 earthquakes. So it doesn't take much imagination to to think that this had an impact as well, and I'll talk about that more. The one really interesting observation that we're still trying to figure out is that so there was ongoing post-seismic deformation being recorded by our GPS stations at Sumatra following the megathrust earthquakes. And so you can see pre-2012, just sort of what you would expect, extensive, long-term, these are near-field stations, so they're mostly after-slip, post-seismic deformation. At the moment that 2012 happened, it basically shut that off. It's almost like it relocked the megathrust, that 2012 earthquake. And if you compare the post-2000 rates now, post-2012 rates now with campaign observations from before 2004, they're pretty similar. This went back to looking like an interseismic deformation field in the near field from 2012. And if that hadn't happened, we would definitely still be seeing very extensive post-seismic deformation there. So Rishav and Sharda are trying to figure this out. Rishav has a lot of thoughts about the role of the LAB and whether that helps to explain everything. In terms of the viscoelastic deformation in the far field, it also had a big impact. So the first three panels are the viscoelastic signatures of these big earthquakes. This is work from my PhD student Grace, working with Kellen Wang and his team. And you can see that in the far field, out at Singapore and Malaysia, we experienced long-term subsidence from these events. And that's something that Singapore cares very much about because it's relative sea level rise. 2012 had a very different signature with uplift in the far field. And something that's been useful about these is it's helped us to constrain the rheology in that back arc area by using far field stations and viscoelastic models. And here's a better plot. We see a pretty weak asthenosphere out there in the back arc, which is interesting because there's been long-term hypotheses that there's high heat flow back in the back arc area. But that 2012 earthquake in this case was quite useful because it really adds a nice constraint that the models even have to fit the little blip that you get in the far field from the 2012 earthquake. So, yeah, it's clear that we have to understand very well the nature of the oceanic plate and the role it's playing. And it will be interesting to see if Sumatra's unique in this respect or whether most subduction zones, we need to be not thinking of the oceanic plate as this passive, rigid thing that doesn't have much to say for itself. So that's one of the big things we've learned from this. We summarized this plus a whole lot of other stuff in this data, this paper. So I'll advertise it here. It was published in December for the 20th anniversary, and it was written by Gina, who's a young Indonesian scientist. Very proud of her for getting this put together. But we tried to pull together all the lessons that we've learned in 2 decades from Sumatra. I obviously want to recognize Paul for this. This is a happy day when Louisa, who was the student who was working with both of us, submitted her thesis. And I also wanted to mention Susilo. I don't know how many people here knew him. I think Paul knew him, but he was very instrumental in a lot of the Sumatra work and unfortunately passed away last month from a heart attack. So I'm remembering 2 people for this. You remember him? Yeah. So very sad. They were both from the good guys club. So remembering him too. So thank you.